Lowell, Massachusetts became a center of the textile industry in the early 19th century, when it harnessed the power of a 30-foot drop in the nearby Merrimack River to run the textile mills. Tamed into a system of locks and canals, the falling water ran under the mill buildings and turned the blades of huge turbines, which powered the mill machinery. When the industry moved south, the mills and turbines were abandoned. But today, we are rebuilding one of the 5 1901 horizontal turbines at the Appleton mills in Lowell, with the goal of generating electricity at a profit. David Wright, the engineer in charge of the turbine renovation, explains how the system works.
When the canal is drained, we can see the openings to the waterways which supply the water to the turbines. This tunnel is the conduit which supplies the water to the turbines. Presently it is empty because the wooden head gates at the entrance to the tunnel are closed. When the head gates are open, this tunnel will fill with water, filling this chamber with tons of water. That water will drop with a tremendous force through the turbines, 13 feet, and enters the turbine through these guide vanes. Behind these guide vanes are the water wheels. There are 2 on this installation. The water wheels are similar to what you think of when you're thinking of a grist mill, but they are a much more advanced technology. They're cast iron, and they are configured somewhat like a propeller. We'll be able to see that on the outside later. The mechanism which controls the amount of water, therefore the amount of power, is a large cylinder inside these guide vanes. When the cylinder is drawn back, water can flow into the turbine These 2 water wheels are mounted on a large common shaft supported by a wooden bearing in the center of this housing. The large shaft is the main transmission device transmitting power through the large flywheel at this end of the turbine. This is the sheave, or pulley, or flywheel, connected by the shaft that runs through the pressure case to the turbine. The sheave will be connected to a leather belt to the electric generator, and when it turns, the belt spins the rotor of the generator. Much of this room is dedicated to the governor, which controls the amount of water to the turbines, thus the amount of electricity produced. This is the pressure case. On the other side of this wall sits the turbine. This gate shaft is connected to the cylinder gates, which we saw before. The gate shaft is connected by these bevel gears and these pulleys and cables to the governor. The governor is the most complex part of the system, since it controls the speed of the turbine by controlling the opening of the gates. It can be operated manually, like this, but the governor is also designed to operate without supervision, automatically controlling cylinder gate openings, thus turbine speed.
To get the turbine into operating shape, one major job we have is to fix the turbine casing. These steel walls contain the force of the water as it rushes toward the turbine, but large areas had simply rusted out. Ed, the job welder, has to cut away the rotted sections before welding and bolting the new steel plates in place. The old turbine needs many mechanical repairs before it can run again. This coupling is a link between the cylinder gates and the governor. It's slipping, so the cylinder gates can't be adjusted properly. To realign them, we first make sure that the gates are in place by positioning them manually with the governor wheel. There are two couplings, in fact, one for each set of cylinder gates at each end of the turbine. To make sure the gates would operate evenly, we go from one to the other and count the number of teeth showing on the rack to measure the distance the gate is opening. Finally, we find we have to go down into the turbine casing to loosen and reposition one gate arm. Then we can hammer it into place. With everything positioned correctly, we are ready to drill a new hole in the coupling. We tap threads into the hole, and secure the coupling with a new bolt. Meanwhile, Ed is winching up a new sheet of metal to replace the rotted out parts he'd cut away. When it's in place, he trims it to the exact size with a torch. Then he pounds it even and clamps it. And finally, he is prepared to weld the seams shut and watertight. Seth is working in the tiny bearing chamber between the two turbines. To get there, he first drops into the main pressure case through a manhole in the top, and then lowers himself into the space between the turbines. In this chamber, Seth is chipping away the layers of crust that have accumulated since the turbine was abandoned in the 1940s. Everything must be cleaned and taken apart to inspect its condition. Our first task is to remove the metal casing from the bearing which surrounds and supports the central shaft. We burn the old bolts, then cool them with water, in order to loosen them so they can be wrenched off. With the upper half of the bearing case removed, the top part of the wooden bearing can be probed for signs of rotting. Now the top part of the wooden bearing is lifted out of the chamber, and we can see the metal shaft, no longer smoothed but pitted and gouged from years of use. The next task is to smooth down the pits and gouges in the shaft. First we sand the shaft directly. Then we mix up a batch of red hand, an epoxy compound, which is applied in a thin coat the length of the shaft. When Ed is finished welding, He must drill holes for the bolts, which will further secure the new sheet of metal to the frame of the turbine case. Burning through the holes in the sheet metal is the next step. Inside the turbine case, Ed slides the bolts into the holes he's just burned through. He tightens the bolts outside the casing with a wrench. Then he welds them in. Next, we sand down the red hand. It seems like an endless task. We take turns and bring in some extra help, sanding until we get down to the bare, smooth shaft, where the epoxy is left to fill in the gouges. Later, we're ready to put back the wooden bearing pieces. The bottom bearing, made of the rare hardwood Lignum vitae, is in good shape, and we can still use it. But first we have to pry it apart. Then we can slide the pieces together under the bearing. We assemble the new pieces of the wooden upper bearing and secure the pieces with these 3 metal rods. Then we lift up the whole assembly and turn it over onto the shaft. The wooden thrust bearing is still usable, so we carefully thread it onto the 3 metal rods. The bearing case cover is fitted on next, and Seth tightens the clamps to secure the wooden thrust bearing. While David tightens the bolts on the bearing case. Ed fits the last piece in place in the pressure case wall. It's getting close to the moment when we're ready to let the water through to turn the turbines for the first time. Seth is ready to put the top back on the bearing chamber when the lights go back on, he can bolt it in. The last step before running the wheel is closing the hole in the top of the turbine case. And we've got an audience. The caulking goes on to seal the hole watertight. It's very well documented. We carry the cover over and bolt it on. When the head gates are first lifted and the water flows in from the canal, you can hear it coming a long way off. It takes some time for the pressure case to fill, so we have time to tie up a bottle of whiskey for a little wheel turning ceremony. Ed checks for leaks in the side of the turbine case. Everybody's waiting for the moment. After the first exhilaration at seeing the wheel turn, David focuses his attention on the clunking noise coming from the turbine. The noise turns out to be a loose runner, which we will eventually have to repair. The next set of repairs we're facing involves the pump and hydraulic system for the governor. The oil pump forces oil into and through the governor, but the copper tubing has long since disappeared and we have few clues as to how it once ran. Since this is such old equipment, we've researched old documents to help us figure out how to rebuild it. We start by dismantling the oil pump to clean it and check the parts for wear. The governor must also be taken apart in order to clean it. This new leather belt connects the main shaft of the turbine with the oil pump so that the revolutions of the shaft can power the pump. These broken teeth make this governor gear unusable, but it's an important part of the mechanism. The gear turns the cables connected to the cylinder gates when the governor is engaged. To find a replacement, we turn to one of the other 4 turbine installations on the property. We locate an abandoned governor exactly like the one we're fixing, and scavenge a replacement gear. Next, we turn to rebuilding the large flywheel. The old wood has rotted and could never stand up to the strain of use. We begin by dismantling one section, half the width of the wheel, uncovering one row of spokes in the process. First, we fit new boards into the staggered spaces between the old boards. This indicator acts as a guide to fit the new boards to match the curve of the giant flywheel. The guiding mechanism can be moved into place along a track. Each board is thoroughly painted with glue before it is fitted into place and screwed in. On the inside of the wheel, the huge spokes were designed for the tighter curve of the smaller wheel. They must be fitted with wedges to the curve of the giant wheel. On the outside of the wheel, we drill holes to recess the bolt heads. We pound the bolts into the holes and secure them from the inside. We take advantage of a day when the canals are drained to place these closely spaced bars, called trash racks, across the opening to the penstocks. The trash racks keep debris from clogging the turbines. Despite our care in rebuilding the flywheel, it's still uneven. We use this lathe to trim down the wheel while it's running. The lathe is slowly cranked across the wheel, then it must be readjusted for the next pass. The leather belt, which will connect the flywheel to the electric generator, is being made in this factory in North Carolina. Each hide is trimmed to size with a massive blade. Then the edges are scraped and beveled to prepare the 3-inch overlap where the pieces are joined. The edges are lined up and painted with glue. The top piece is turned over and the overlapping edges are fitted together and sealed. Then the joined edge is pushed forward into the clamp. Slowly, the belt takes shape. After the belt has been installed and running, we find that it is stretching. So in order to shorten it, we stop the wheel and secure the belt with clamps, and cut away a piece of the belt. Next, the newly scraped edges of the leather are painted with glue and clamped together. Meanwhile, we're almost finished wiring the switchgear, the panel which controls the power flowing through the system. Then it's time to start up the wheel to spin the generator coils. Inspectors from Mass Electric arrive to make sure that everything is wired correctly. And the flashing light bulbs show we are generating power as the wheel turns.